Welcome to Tomorrow Unveiled. It is Monday, February 9th, 2026. If you've been following the headlines or even just glancing at the tech sector's market cap this morning, you know that we have officially survived the first month of what historians and certainly the venture capitalists in my network are aggressively branding the year of physical AI.
It really does feel like the branding is finally catching up to the engineering reality. For the last few years, we've been in this sort of strange holding pattern. We had the intelligence in the cloud, the big language models, and we had the hardware in the factories, but they weren't really talking to each other in a meaningful way.
That's the perfect way to frame it. I was reviewing the timeline on the way into the studio, and it just struck me how bifurcated the landscape has been. I mean, since the whole GPT-4 era kicked off, AI has been almost completely synonymous with disembodied intelligence. It was a chat box. It was a blinking cursor. It was a generator that could write you a sonnet or code a website. But, if you asked it to make you a cup of coffee, it was helpless. It had no hands.
Exactly. It was a brain in a jar. It's a very, very smart jar, but a jar nonetheless. And on the flip side of that, we've had robots for, 50 years? But those weren't intelligent agents. They were, at their core, just automation scripts. A robotic arm in a car factory in, say, 2020 was essentially a glorified printer. It just followed a pre-programmed coordinate path. If you moved the car door 3 inches to the left, the robot didn't adjust.
Oh, not at all. It would just smash right through the window because its programming said, move to coordinate XYZ.
Right. Blind, deaf, and bolted to the floor.
Blind, deaf, and dangerous. But looking at the stack of research we have for today, that era is effectively over. We've crossed some kind of massive threshold where the brain has finally been downloaded into the body. We aren't just looking at generative AI anymore. We're looking at embodied intelligence. These are agents that can perceive the physical world, reason about causality and physics in real time, and actually act upon it.
And that transition from, text to pixels to action, that is what's really defining the 2026 landscape. We're seeing robots that don't just follow scripts, they learn by watching us. They can understand the semantic difference between a dirty plate and a clean plate. Not because one has a barcode, but because they actually understand the concept of dirt.
That distinction right there is the core of what we need to unpack here on Tomorrow Unveiled. We have a massive lineup of developments to cover. First, we have to talk about the Moe robot from DroidUp, which is currently causing a full-blown stir on social media, not just because of its movement, but because it apparently has warm skin.
Which brings up a fascinating and kind of uncomfortable discussion on biomimicry versus the uncanny valley.
Definitely. We're also going to do a deep technical dive into the Helix brain and the new Figure 03 robot. I want to get into the weeds on the shift from transformers to Mamba and CAN architectures, because that seems to be the only reason these things can run without a supercomputer tethered to their backs.
It's the efficiency breakthrough. Without it, the economics just don't work.
And speaking of economics, we have to address Elon Musk's von Neumann claims, robots building robots on Mars, and then contrast that with the actual on-the-ground reality of blue-collar bots that are moving boxes at Spanx warehouses right now.
That's the story that actually matters for the GDP this year. The big shift from demo to deployment.
So that is our mission today, to strip away the marketing gloss and look at the engineering and the economics. Is physical AI the industrial revolution of our time, or is it just a really, really expensive, capital-intensive bubble?
Well, based on the deployment numbers our research team is seeing, I think that bubble theory is becoming a lot harder to defend.
Let's get into it. I want to start with the visceral reaction the public is having to DroidUp's new unit, Moya. You've seen the videos circulating.
I have, yeah. It's hard to look away.
DroidUp, the Chinese robotics startup, they debuted Moya just 48 hours ago, and the internet is, freaking out is the technical term. But it's not the usual, wow, cool robot reaction. It's this weird mix of awe and genuine discomfort. And it really seems to all come down to the movement. They're calling it a biomimetic AI robot.
Right. And that word biomimetic is doing a lot of heavy lifting there. In traditional robotics, engineers solved for stability using what we call zero moment point control, or ZMP. You're essentially programming the robot to keep its center of mass perfectly balanced over its feet at all times.
And the result is that classic robot walk, right?
Oh,
Knees always bent, hips are rigid, feet kind of shuffle.
exactly. It's safe, it's stable, but it looks like the robot is, well, sneaking around, or frankly, like it has a full diaper. It's just not natural.
It's mechanical. You instantly identify it as not alive. There's no ambiguity.
Correct.
Yep.
But Droid Up, they took a completely different approach. They used reinforcement learning trained on just massive amounts of human motion capture data. So they didn't tell the robot, keep your balance. They told it, minimize energy expenditure while moving forward, which is, exactly what biological evolution did to us over millions of years.
So it converged on the same solution that nature did.
Precisely. The research team notes that Moya achieves a 92% human gait accuracy. This includes all the subtleties, the slight pelvic tilt, the heel strike toe-off mechanics, the passive swing of the arms. It's incredibly efficient, but to the human observer, it triggers a powerful pattern recognition match deep in the brain.
And that's the 92% that gets you. If it were 50%, it's a machine, it's a toy. If it's 100%, it's a human. But at 92%, it sits right in that cognitive dissonance zone. You see it from the corner of your eye, and your lizard brain says, human. Didn't know. Then you look directly at it, and you see the silicone and the seams and the metal.
And that is the textbook definition of the uncanny valley. It's a prediction error in the brain. Your visual cortex predicts biological behavior, but it receives synthetic data. That mismatch creates a feeling of revulsion or even threat. It's an evolutionary defense mechanism, probably to help us avoid corpses or diseased individuals.
Which makes DroidUp's other design choices even more controversial. I mean, they didn't just stop at the walk. They gave Moya micro-expressions, tiny little muscle twitches in the face, and this is the part that I find most fascinating, warm skin.
The thermal regulation system.
It's not just regulation, though, is it? It feels like a user interface. Why does a robot need to be 98.6 degrees Fahrenheit? Is there a functional reason for that, or is this just designed to mess with us?
There is a very specific functional reason, but it completely depends on the use case. See, Droid Up isn't targeting the factory floor with Moya. They're not going after logistics. They are targeting the high-touch economy, healthcare, elder care, special needs education. And if you are designing a robot to help an elderly patient out of a bath or to hold the hand of a child with autism during a stressful therapy session, the material properties matter a lot.
Cold metal induces a recoil response, a flinch.
Exactly. We instinctively associate cold with dead or clinical. We associate warmth with life and safety. The researchers at Droid Up are making a big bet. They're arguing that to build trust in a caregiving setting, the tactile experience has to be biological. They are prioritizing emotional connection, or effective computing, as it's sometimes called, over raw industrial durability.
It's a fascinating pivot. We always think of robots as tools. A hammer doesn't need to be warm. A drill doesn't need to be warm. But if the tool's job is to replace a human nurse or a companion, then yeah, maybe it does.
That's the gamble they're taking. But it can backfire spectacularly if the visual processing doesn't match the tactile one.
Right. And it seems like it is. Our research team pulled a bunch of comments from the initial launch video reactions. The netizen response is visceral. One user wrote, and I'm quoting here, "If she takes 2 steps near my bed at night, I'm throwing her off the balcony." That's not a critique. That's a fight-or-flight response.
It triggers the intruder alarm in the amygdala. And this is the central challenge for 2026. The hardware has become so good at mimicking biology that it's tripping our own ancient biological alarms. When robots looked like trash cans, like RTD2, we loved them. They were cute, they were safe, non-threatening. Now that they're starting to look like us, we view them as potential rivals or threats.
It's the invasion of the body snatchers problem. But I wonder if this is just a temporary cultural hurdle. I mean, think about the first time people heard recorded voices on a phonograph. It was terrifying. People thought they were hearing ghosts in the machine. Now a recorded voice is just background noise at the grocery store.
That's a very valid historical parallel. Exposure therapy works on a societal level. If Moya is in your grandmother's nursing home and she loves it, if it helps her walk and keeps her from being lonely, you might stop seeing the creepiness and start seeing the utility. In fact, I'd argue that in 5 years, warmth might actually become a premium feature. The cheap robots will be cold and plasticky. The expensive luxury robots will be warm.
Upgrade to the Pro model for thermal haptics, I can absolutely see the marketing copy now. But let's bridge from this.
Yeah.
We've talked about the body, the biomimetic gait, the skin, but a body that moves like a human is, well, it's just a creepy mannequin if it has the brain of a calculator.
Correct. The uncanny valley of movement is being solved. Now we have to solve the uncanny valley of intelligence.
This brings us to the brain upgrade. And this is where the real technical leap of 2026 is actually happening. We are moving from large language models, LLMs, to what the industry is now calling VLA models, vision language action.
This is the critical architectural shift. We spent the last few years perfecting the vision language part of that. You could give an AI an image, and it could describe it with incredible detail. I see a red apple on a wooden table in a sunlit room. But that's passive observation. The action part is the revolution.
So explain the difference for us. In a traditional LLM, like ChatGPT, the output is a text token, a word. In a VLA, what is the output?
In a VLA, the output isn't just a word, it's a vector. It's a set of coordinates and motor commands. The model takes in pixels, a live video feed from the robot's eyes, and directly outputs the electrical signals to contract the muscles of the hand. It completely bypasses the need for a separate, hard-coded motion planning layer of software.
Okay, so previously you'd have a vision system that says Apple located at coordinate X, and then a completely separate piece of code would have to calculate all the joint angles to reach X. But now, the neural network just intuits the movement the same way it intuits the next word in a sentence.
That is the perfect analogy. It learns physics through observation, not through equations.
Yeah.
This is why the new Figure 03 robot, which is running their Helix brain, is such a big deal. It's operating entirely on this new VLA architecture.
Let's talk about Figure 03. We've been tracking Figure AI for a while now, but this latest update feels fundamentally different. The hardware changes alone are pretty significant. They put cameras in the palms, for instance.
The palm cameras are just a brilliant solution to what engineers call the occlusion problem.
Yeah.
If you're a human and you reach into a deep cupboard, you can't see what your hand is doing. You have to rely on proprioception, your innate sense of your body's position in space. Robots aren't great at that yet. But by putting eyes in the hands, the Figure 03 has perfect visibility right at the point of interaction. It can literally see the handle of the mug as it grabs it.
But the hardware is only as good as the software processing that signal. And this is where I want to get into the deep tech papers our team unearthed. We aren't just talking about bigger transformers here. The research is pointing to things like Mamba architecture and CANs or Kolmogorov-Arnold Networks.
This is the stuff that gets completely glossed over in the mainstream press, but it's the only reason these robots can function in real time without being wired to a server farm.
Okay, so let's break it down. Why abandon the transformer? I mean, ChatGPT runs on transformers. It seems to work just fine for that.
Transformers are incredible for language, but they have a fatal flaw for robotics. Their compute cost scales quadratically with the length of the input sequence. We call it the O of n squared problem.
In plain English.
Imagine you're reading a book. A transformer, to understand the context of a new sentence, has to essentially reread every single previous page every time. So as the book gets longer, its reading speed slows down to a crawl. For a robot, that context is the video feed of the last minute of its life. If it takes 500 milliseconds to process that history, the robot lags. It freezes. It stutters.
And in the physical world, a 500 millisecond lag means you've already dropped the plate or you've fallen down the stairs.
Exactly. It's a non-starter. So enter Mamba. Mamba is based on a different concept called state space models, or SSMs. The core innovation here is that it compresses the entire history, the entire context, into a fixed size state. It doesn't need to look back at the raw video history. It just carries a compressed memory of that history forward in time.
So instead of rereading the entire book every time, it just keeps a running summary in his head.
A perfect analogy. And mathematically, this scales linearly, meaning it doesn't matter if the robot has been running for 10 seconds or 10 hours. The processing speed for each new frame is the same. This allows for what we call linear time sequence modeling. It's what gives the Figure 03 that fluid, jazz musician-like improvisation. It can remember that it picked up a towel 30 seconds ago. That's a long horizon dependency without slowing down its current motor control one bit.
That explains the fluidity. That makes sense. Now, what about the CANs? Kolmogorov-Arnold Networks. It sounds like something from a 1960s Soviet math journal.
It effectively is, but it's been modernized for 2026 machine learning. The CAN architecture is a direct challenge to the traditional multi-layer perceptron, or MLP, that we've used in AI for decades. In a standard neural network, the neurons, the nodes, have a fixed activation function. Think of it like a simple switch. The learning all happens in the strength of the connections between them, the weights.
Okay. And CANs flip this on its head.
CANs move the learnable function to the edges, the connections between the nodes. They use these complex, learnable mathematical curves called splines. Without getting too bogged down in the calculus, the end result is that cans can learn highly complex patterns with significantly fewer parameters.
Fewer parameters is the key phrase there, I'm guessing.
It is. It means the brain is smaller. It's more compact. It requires less memory and, crucially, less electricity to run. This is absolutely critical because you can't put a liquid-cooled data center inside a robot's chest. You need a brain that is incredibly smart, but also incredibly lightweight and efficient. Canids, combined with Mamba, are allowing us to run high-level intelligence on local onboard chips.
So this is the convergence we were talking about. You have the VLA model for the overall understanding, the Mamba architecture for speed and memory, and now CANs for efficiency. It's a completely new software and hardware stack compared to what we had even 2 years ago.
It's the difference between a brute force approach and an elegant, optimized one. That's why 2026 is the inflection point.
It's just incredible engineering, but I want to pause here for a second. We've talked about the how, the biomimicry, the neural architectures, but we need to spend some time on the why. Why are we pouring billions and billions of dollars into this? What is the economic engine that's driving this whole revolution?
It's the labor market, pure and simple, the global demographics.
Before we pivot to the blue-collar bots and the reality of the warehouse floor, I just want to take a quick moment to acknowledge our community. We are unpacking some really dense concepts today, Mamba, KAN's VLA, and if you're still with us, you are exactly the kind of curious mind we make Tomorrow Unveiled for.
We really do appreciate you diving this deep with us on this.
If you're watching on YouTube and finding this breakdown valuable, if you prefer this to the surface level hype, please hit the like button and subscribe to Tomorrow Unveiled. And consider hitting that new hype button. It really helps the algorithm find other people who want to understand the mechanics of the future, not just the headlines. And of course, be sure to turn on notifications so you never miss an update on the future.
And for our audio listeners on Spotify or Apple Podcasts, we haven't forgotten you. If you could take just 10 seconds to leave a rating and a review for Tomorrow Unveiled, it makes a massive difference for us. It helps us secure the resources to keep this research team digging into these technical papers.
Absolutely. Okay, so let's talk business. Let's talk about the workforce, because there's a very, very specific narrative being pushed by the biggest player in this space.
You mean Elon Musk and the von Neumann machine?
Right. Musk has been incredibly vocal about the Tesla Optimus robot. He recently called it a von Neumann machine. Now, John von Neumann was a genius, a polymath, but he wasn't building Toyotas. What does this term actually mean in this context?
So von Neumann, back in the 40s and 50s, proposed the concept of a universal constructor. It's a theoretical machine that, if you give it a supply of raw materials, can build a perfect copy of itself. It's a self-replicating machine. Musk is invoking this idea to suggest that Optimus isn't just a product, it's a catalyst for exponential growth.
So the idea being, you don't try to build 100 million robots in your factories. You build one factory that builds robots, and then those robots go out and build the next factory.
Exactly. It's the concept of recursive self-improvement and self-replication. It's a powerful idea. Musk's claim, which he posted on X, naturally, is that Optimus could eventually build civilization by itself on Mars. You send a single landing craft with a few units, they mine the Martian ore, they refine the steel, they 3D print the parts, and they assemble more units, which then build more factories, and so on.
It's the ultimate science fiction dream, and it's also the ultimate economic cheat code. Musk is predicting a $5 trillion market cap for humanoids by 2050 based on this idea that labor becomes effectively free. If a robot costs only the price of its raw materials plus the energy to run it, and it can do any job a human can do, then the cost of all goods and services plummets to near zero.
That's the classic post-scarcity economic argument. But we have to apply a very serious discount rate to Musk's timelines. He's famous for his optimistic scheduling, to put it mildly. Mars colonization via autonomous robots is a 2040 or maybe 2050 scenario, if we're lucky.
Right. I want to know about Monday morning, February 2026. What is the reality of the blue-collar bot today? Because it's not building civilizations on Mars, it's moving totes in Georgia.
Let's look at Spanx, the shapewear company.
This is the reality check that we need for Tomorrow Unveiled. Agility Robotics has deployed their robot, Digit, at a Spanx facility in a town called Flowery Branch, Georgia. This isn't a demo video with sped-up footage and perfect lighting. This is a real-world deployment.
And the job it's doing is incredibly, almost painfully mundane. Digit is taking these yellow plastic bins totes in logistics jargon off a robotic cart and placing them onto a conveyor belt. That's it. It's what's known as the last meter problem.
It sounds boring, but economically, it's a huge bottleneck in the supply chain.
It's a massive bottleneck. We have automated the trucks that bring goods to the warehouse. We have automated the sorting machines inside. But that gap, that last meter between the cart and the conveyor belt, almost always requires a human to bend, twist, lift, and place. It's repetitive, it's ergonomically dangerous work, and it has incredibly high turnover rates.
So Digit fills that specific gap. But let's do the math on this. I've seen the sticker price for these advanced humanoid robots hovering around $250,000 to buy one outright. If I'm a warehouse manager, why would I possibly pay $250,000 for a tote mover when I can hire a human for $20 an hour?
Because you aren't paying $250,000. That's the old capital expenditure model. The entire industry has shifted to raise less robots as a service.
Like SaaS for software, but for hardware. A subscription model.
Exactly. Spanx isn't buying these units. They're almost certainly leasing them. So let's break down the unit economics of that. A warehouse worker making $20 an hour actually costs the company closer to $30 or even $35 an hour once you add payroll taxes, insurance, benefits, and training costs. So that's roughly $60,000 to $70,000 a year for a single human worker on a single shift.
Okay, so that's the benchmark that the robot has to beat.
Right. Now, Agility leases the robot. Let's conservatively estimate the lease at around, say, $3,000 to $4,000 a month. That's $36,000 to $48,000 a year. So right away, you're undercutting the cost of a human. But here is the real kicker. The robot can work 2 shifts, or even 3.
It just needs a battery swap. It doesn't need breaks or a lunch hour.
Or just a quick charge on its dock. So now that $48,000 a year robot is replacing $120,000 with human labor for 2 shifts. The ROI, the return on investment, is suddenly well under 12 months.
But wait, you have to factor in the hidden costs. Robots break down. They get confused. They need teleop support, where a human in a control center has to jump in remotely to fix a glitch. That costs money.
That's true. And that intervention rate is the key metric everyone in the industry is watching right now. If a human has to intervene every 10 minutes, the economics completely collapse. But the reports our team has seen from Agility and Figure show intervention rates dropping drastically. They're approaching 1 intervention per several hours of operation for these simple, repetitive tasks. Once you cross that threshold, the RAAS model becomes a money printer for the logistics company.
And that explains the production numbers we're seeing. This isn't just a boutique experiment anymore.
No, not at all. Agility's RoboFab in Oregon has a stated capacity for 10,000 units per year. Their main Chinese competitor, Agibot, just announced it shipped its 5,000th unit. We are seeing the industrialization of the humanoid form factor. This is the Model T moment for robotics. We aren't handcrafting them anymore. We are stamping them out on production lines.
It's a very sobering thought. We are literally watching the automation of the physical world happen in real time. But while the warehouse is all about raw efficiency and ROI, the home market is about something else entirely.
It's about trust and safety.
Let's pivot to the household. Because companies like Figure and Tesla, their end game isn't just the warehouse. They want these things in our living rooms, in our kitchens, and that requires completely different design philosophy.
Absolutely. You cannot put a 300-pound industrial robot made of cast iron and sharp edges next to a toddler. It's a recipe for disaster. That's why the Figure 03 looks so fundamentally different from its industrial predecessors.
It's soft. I mean, it's covered in fabric.
It's covered in textile. It uses foam padding under the fabric. This is soft robotics principles being applied to a humanoid form. It's designed to be compliant.
Compliant is an engineering term. What does that actually mean for the listener?
In physics, compliance is the inverse of stiffness. If you run into a steel beam, it is non-compliant. It doesn't move, you break. If you run into a mattress, it is compliant. It absorbs the energy of the impact. The actuators and joints in the Figure 03 are designed to have give. If the robot's arm accidentally hits an obstacle, like your shoulder, it doesn't just power through it, it yields, it stops.
That seems absolutely critical. And I see here in the research that they are pushing for ISO functional safety standards. What is ISO 13482?
Yes, ISO 13482 is the international safety standard specifically for personal care robots. It's a huge deal. It defines the performance levels required for safety-critical parts of the system. It dictates things like mandatory force limiting. The robot has to know the difference between the force required to open a stubborn pickle jar, which is high force, and the force required to hold a baby's hand, which is very low force. And it needs hardware little limiters that make it physically impossible to crush the baby's hand, even if the software completely bugs out.
So it's the guardrail concept. The software can be smart, but the hardware must be safe by default no matter what.
Exactly. And beyond the physical safety, there is the intelligence scaling problem.
Hmm.
This is where this shared brain concept, I think Figure calls it kinetic QAI, comes in. This is arguably more powerful than the hardware itself.
This is the fleet learning idea, right?
Right, so imagine you buy a robot for your home. You spend a week teaching it how to fold your specific brand of laundry or how to load your weirdly shaped dishwasher. In the old days, that knowledge, that data, stayed in that one robot.
And now,
Now, that learning is uploaded to the central cloud, anonymized, of course, and it's integrated into the base model that powers all the other robots. So suddenly, every other robot in the fleet, whether it's in Tokyo or Berlin or New York, instantly knows how to load that specific dishwasher model.
it's the scene from The Matrix. I know Kung Fu.
It is. It's what the tech industry calls the flywheel effect.
Yeah.
The more robots there are in the world, the more data they gather. The more data they gather, the smarter the entire fleet gets. The smarter they get, the more useful they are, so more people buy them, which generates more data. It's a positive feedback loop that accelerates exponentially.
That is formidable. It means that the rate of improvement we see today is the slowest it will ever be from this point forward.
That's a chilling but very accurate way to put it.
Before we wrap up here, I want to make sure we don't succumb to what I'd call humanoid bias. We spend so much time talking about robots with 2 arms and 2 legs because that's what we look like. But sometimes legs are absolutely the wrong tool for the job.
Form has to follow function. If your job is to perform knee surgery, you don't need a robot that can walk around the room. You need a robot that can cut bone with sub-millimeter precision.
This is the specialist robot market. Our team highlighted a new device from Stryker called the Mako RPS. This is a handheld robotic system. It's Robotics.
Collaborative robotics. The human surgeon holds the tool, but the robot controls the fine movements. Think of it like lane keep assist in your car, but for a bone saw. It creates a haptic boundary, a virtual wall. If the surgeon tries to cut outside the planned area, which is based on a preoperative CT scan, the robot physically resists. It won't let you make that mistake.
That saves lives. Or, at the very least, it reduces recovery time and improves outcomes. And it's happening in operating rooms today. It's not a sci-fi promise for 2030.
And in cardiac care, we're seeing AI that can analyze CT scans and predict heart attack risks that even experienced human radiologists miss. The specialist bots are quietly revolutionizing healthcare, while the humanoids are the ones dancing on TikTok and getting all the attention.
It's a good reminder that physical AI isn't just one form factor. It's a whole ecosystem of different tools for different jobs.
Yeah, it is. But the convergence is the overarching theme. Whether it's a surgical tool or a warehouse poke mover or a warm-skinned nurse, they are all benefiting from the exact same underlying breakthroughs: the VLA models, Mamba level efficiency, and improved battery density.
So let's zoom out. We've covered the body with Moya, the brain with Helix, the job with Digit, and the home with Figure. It really feels like February 2026 is the moment where all these different vector lines finally crossed.
It really is the convergence point. The hardware has, at long last, caught up to the software. The muscles have caught up to the brain.
I want to leave our listeners with a thought that kind of brings us full circle back to the start. We talked about Moya's warm skin and the deep discomfort of the uncanny valley. We also talked about robots learning from us via the shared brain.
We are the training data.
That's the phrase that really stuck with me from our research. We are the training data. If these robots are entering our homes and they are watching how we interact, how we speak to each other, how we argue, how we care for our children and our pets, they are building their fundamental model of humanity based on us.
That puts a tremendous amount of responsibility on us, doesn't it?
It does. I mean, if we treat them like trash, if we yell at them or kick them because they're just machines and they are learning from every single one of those interactions, what kind of intelligence are we actually building?
We might be inadvertently teaching them that hierarchy and dominance are the primary modes of interaction in the world. And that's a very dangerous lesson to teach a superintelligence.
Conversely, if we treat them with, I don't know if respect is the right word, but maybe dignity.
Or just basic civility.
Civility. Maybe we're teaching them through our own actions to be civil. This guest versus appliance debate isn't just about etiquette. It might actually be about AI alignment.
It's a mirror. In the end, they are just going to reflect us back to ourselves.
That is a heavy, but I think a very necessary place for us to land. We'd love to hear your take on this. Living with a robot that has warm skin, is that a comfort or a horror show? And are you ready to be a role model for a machine?
I'm definitely going to be very polite to my toaster this week, just in case.
Good strategy. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think. Let's get the discussion going. I'm host speaker.
I'm expert speaker.
And this has been Tomorrow Unveiled. See you in the future.